matrices. Fundamental matrices. So no matter how I look at this section, it's almost, it's a bit, it's sort of a strange section in that, in some sense, nothing new is presented in this section. Okay, that is, there's no new technique on how to solve differential equations. It's rather sort of an interpretation of stuff that you have before. Okay, and so when you look at it, you're going to say, but don't we already have all the solutions? And you know, why would we, you know, it's going to seem sort of strange, but it's rather sort of a way of interpreting what we had before. And further, it leads into the Jordan canonical form in the next section. So I think that's the main point of it. Okay, so, but yeah, it's more like sort of like a reinterpretation of previous results. Okay, so let's start off with a couple of definitions. So you have, as usual, a homogeneous system. A homogeneous system, and here is our first definition. If you have x1, x2, xn, right, and each of these is a function, right? So these guys, say, are a fundamental set of solutions of the system H. Then let Cx be the matrix with those guys as the columns. So you create a matrix function. You create a matrix function where these guys are columns. Okay. We call this thing C a fundamental matrix. Fundamental matrix for that system. Okay, so all it is a matrix where the columns are solutions, right? Where the columns are linearly independent solutions of that system. Okay. And so this is a function, right? And let me make a couple of remarks. So notice that if you take that system and if you take that matrix function and you differentiate it, right? That is, well, that will end up being differentiating everything term-wise. That turns into, as you expect, AT CT. Right? Because each of the columns satisfies that x prime is ax prime. Right? So you differentiate everything, you get a times the columns. Is that right? Okay. So notice that happens. Right. So this matrix value function satisfies its own matrix value differential equation. Right. Like here we're looking for a vector, a vector solution to this vector differential equation, and we put these all together, we get a matrix, and that matrix satisfies its own differential equation, not surprisingly. Right? Just one, I saw Harry, but I didn't see Dan today. And also notice, so notice that, and also notice that if we take any vector x0, then if I take C prime x0, well, that's the same thing as AT CT x0. AT CT x0, right? Right. Let me put brackets on it, make it more suggestive. Okay. And so, what do you see if I take any vector and I hit it with this matrix, right? I get something. I get a vector. Right? I get a vector value function. Right? Let's call this xt. I get some xt, and what do you see about this xt? Well, Georgia. Its derivative, right, this thing here is its derivative, right? Its derivative equals.
It's like e to x.
Yeah. And so what you see is that you get a solution. You get a solution, right? If I take choose any vector. Suppose you have a fundamental matrix. Right? You have this matrix of solutions, right? I take any vector and I hit it with this thing. I get a new vector. I take any constant vector and hit it with this thing, right? I get something. It's a function of t. Right? It changes with t. And I notice if I differentiate this guy, oh look, I get x prime is equal to at xt. Right? In other words, if I take any vector x, then ct x naught is a solution of our original homogeneous equation. There seems to be an error of confusion.
Why again do you say that x naught, which word d? I don't know, what's that variable?
C, oh, C of the sign.
Why is that x of t? Again.
Oh, I created that way.
Okay.
Okay. Take any vector, and then take any vector block, and then let this thing be defined to be the fundamental matrix times that fixed vector. Okay. Then that thing.
And the fixed vector is just constants, right?
Yeah. Yeah.
So when you take the derivative, it just that's why you still x naught.
I wrote this.
Can I put prime? Make a derivative of your x thingy?
Where?
Let?
No.
No?
No. No. Let this be that. Let me read.
Oh, okay. Never mind, yeah.
Okay, let me rewrite this. Fix any vector x block, and then let xt be c times that thing. Okay? And then let's look. X prime t, well, that's c times t x naught, right? X naught is a constant. X naught is a constant vector, so when we differentiate, we're just going to differentiate this part. Right? But this, by our first observation, is at ct x naught. Right? Ct x naught is x. Right? So we've created a solution of our original equation. Right? X solves H.
We did just a totally circular argument. Like I don't know. I'm not sure how this possibly yet. I feel like so C
In
is
some sense, yeah.
C is just a fundamental matrix.
Yes. And so what we did is we're taking it's not a surprise, right? We're taking a linear combination of right? If we take any vector Well, what we're getting is a linear combination, right? This new guy, it's not really new, is just a linear combination of those solutions, right? And all we're saying is that that linear combination is still a solution to the homogeneous system. You're right. And you're going to say that again and again during this section. Right? We haven't done anything new. This is just a different way of looking at it.
Can you repeat that one more time?
Yes. So Blake is pointing out correctly that all we're saying here is that if you take a bunch of solutions and then take any linear combination of them, right? Maybe if I call this C naught, it'll make it even more suggestive that this is just, just some combination, right? Some combination of the columns of this is just a linear combination of the columns of C, but C's columns are the fundamental set of solutions of this thing, right? So you're taking a linear combination of the fundamental set of solutions, that's still a solution. Right? You knew that already. Right? You knew that. So we're just writing it slightly different way. Okay. Second definition. If P is a fundamental matrix, or H, and Phi at some time is the identity matrix, then we call Phi the special fundamental matrix, the special fundamental matrix for H, for time T naught. So it's just a fundamental matrix that happens to equal the identity matrix at that particular time. And note that in that case, P satisfies not only that P prime equals a Phi, but also that Phi at a particular time equals the identity matrix. Right? So it satisfies an initial value problem. Right? It satisfies an initial value condition in addition to the matrix differential equation. And maybe you recognize what Phi is the analog of. Let's think, if this were at time 0, Phi prime is a Phi, and Phi at time 0 is I. What is that in the world of numbers, like scalars? You got a function, its derivative is some constant times itself. E. Right? This is the analog of e to the 18. Right? At time 0, it's going to be 1. Right? When you differentiate it, you get a times itself. Right? And what we'll see next time is that you can actually define sort of the exponential function of the matrices, and we use it to explain what we did before.